Welcome to Static Equilibrio, Structural Engineering and Connection Design. Let's get started with Structural Steel Connection Design with Idea Statica. So, why Idea Statica for Structural Steel Connection Design? So, there are two approaches basically conventional connection design, and a component based finite element method, which is implemented in Idea Statica. So this conventional connection design is based on the formula-based software or the spreadsheet. You might have aware that there are certain sets of formulas which needs to be satisfied, and the connection capacity will be the minimum of those capacities or those checks. These checks may be prying of bolts, stiffener bending, web crippling, web bending, flange bending, shear yielding, or shear rupture. So there are series of checks needs to be satisfied, and all these checks or all these formulas are available in the standard textbooks or manual or design guides. So all in all, here in this particular approach, there is a lack of generality, and lengthy arithmetic checks are there. One cannot view the 3D deformed shapes when the connection is analyzed, which would have help the designer or the user to conceptualize his thinkings or take some decision based on the outcome. So in this particular approach is somewhat mechanistic or mechanical approach with regards to the formulas that are presented in a variety of the textbooks, manual, design guides, and this is a geometry dependent approach. When the geometry there is a slight change in the geometry, then this will not work, or you have to update or add some checks manually to satisfy the connection design. So this particular approach leads to the uneconomical or unsafe design sometimes, because it doesn't capture the criticality to its first place. So opposed to this particular approach, which is finite element approach implemented in Idea Statica, this is developed or devised by Professor Wald and his team at Czech Technical University at Prague and Brno University, and they come up with the CBFEM component-based finite element method as a synergy between strong FEM solver and various FEM components utilized in connection design. The components are basically the end plate, stiffeners, various stiffener, doublers, plates, bolts, fails. All these are the components which are discretized into the layer of mesh in order to estimate the strain and stress relationships uh, in various plate elements. Then the bolts are idealized as a nonlinear spring with appropriate stiffness based on their diameter and uh, stresses. Weld are idealized as a multi-point constraint so that to estimate the forces in it. The strain limit is restricted to 5% as per the codal requirements, and stress are limited to the yield stresses, which is a user-defined stress. So this particular approach has got a flexibility to modify or the geometry at any particular time. Any connection can be modeled and analyzed and designed in this software. The basic difference or the main difference between these two software, or the approach, you can say the design approach in a connection design, is that the strain limit is restricted to 5% as per the codal check, and the stress is yield stress. These are the basic checks which is performed in Idea Statica, which gives it edge over this formula based spreadsheet or the software. Once these two checks are satisfied, all the checks or the formulas steps get satisfied. So these two conditions needs to be satisfied, and everything fall in at right place. So and further, there are the bolt checks and bearing checks, weld checks. Everything is done as per the respective codes and their clauses. The detailed calculation report is can be extracted based on the various country codes, which is American, European, Indian, Chinese, Russian, Australian, and Singaporean. So all this country code, virtually everything is covered in this single software. Uh, whereas in case of this particular software based formula based software or the spreadsheet, you cannot do not have that flexibility or the flexibility to analyze the connections with other codes. You need to either develop your own spreadsheet, or you need to purchase another licenses to cover these codes in that particular software. So all in all, you can see in a next slide how this Idea Statica is a powerful tool uh, in the hand of a connection design engineer. In Idea Statica, you can create the connection from scratch or import it from any other software. It means that Idea Statica offers the interoperability with other software like Tekla structure. It means that you model the connection in Tekla structure and export it in Idea Statica. Again, you design this connection in Idea Statica and again export it to the Tekla structure. So this two-way interoperability is available in Idea Statica. Similarly, the analytical software like SAP 2000, StatPro, RISA, or STRAP, Midas. So all these analytical or design software, you can export the joint along with their forces of various load combination. You directly export to the Idea Statica to check this particular connection for the actual forces. Similarly, the Autodesk Revit and SCADA is that portability is also available in Idea Statica. Apart from that, there are many ready-made templates available in Idea Statica because Idea Statica has got the rich library. There are different classes which are further categorized into the geometry and design. So, for example, if these classes of beam and column, you will find that numbers of various combinations are available. For example, in this particular classes, the beam and column connection on column flange, similarly on column web, and there are various permutation combinations are available. And further, under each geometry, you will find the series of pre-prepared templates are available, which just need to modify it as per your needs. You can change the section size, you can change the thickness of the plates, you can change the bolt diameter, weld size, and apply the forces and design the connections. Similarly, you can see the classes are for the beam to beam, vertical bracing, base plates, and 3D joints. Further, there is a timber designs also, which we normally don't use here. You can see there are various country codes. Almost 8 countries are covered uh, in this Idea Statica software. We will see the short video where you can see the available templates are available and how to use this template in your design. So there are different options or analysis and design options available in Idea Statica. You can see there are EPS, ST, CD, DR, FAT, FIR, HT. These are the analysis options where you can design and analysis and analyze and design your connection. EPS is a normal stress strain analysis which we normally use in any connection design. Then there is a stiffness analysis wherein you can check whether your joint has got sufficient stiffness or rigidity, and thereby you can classify your joint into rigid, semi-rigid, or uh, pin pin joint. So this is a stiffness analysis options is available in Idea Statica. Then there is a capacity design, and capacity design is a part of seismic check to ensure that the joint has sufficient deformation capacity. And the goal of the capacity design is to ensure that the building exhibits controlled ductile behavior in order to avoid collapse in a design level earthquake. So this capacity design option is available as a CD, you can see. Then there is a design resistance. It means that you model the connection in Idea Statica and estimate its load carrying capacity or moment carrying capacity or shear carrying capacity. So where you can see that with respect to the member capacities, where what is the connection capacity of the connections. Then there is a FAT fatigue analysis. Then FIR is a fire analysis, and HT is a horizontal tie, or you can say this particular analysis is used in progressive collapse. So these types of analysis options are available. We will see in coming videos that how to utilize this various analysis option into our connection design. Then how to interpret the result in Idea Statica. So once you model the connection, apply the loads and run the software, once the connection is analyzed or designed, then these four lines get displayed at the top left corner, where you can see these green tick marks are there, which indicates that the connection is passed. You can further see that analysis is performed to its 100%. It means that there is no non-conformity or a singularity exist in the connections geometry, and everything is okay. Then there is a plate where you can see it is passed and the ratio is zero point 0.2 with respect to 5%. 5% is a limit set as per the codal provision, which is strain limit. So this particular check for the plates is for the plastic strain check. And here in particular case, you can see it is just zero point 0.2 with respect to 5%. This indicates that there is a room for optimization so that this particular value can be say 3% or 2%. Then there is a bolt check where you can see 61.5% bolts are stress with respect to 100%. This also you can reduce the size of the bolts and optimize the connection. Weld is stressed to its 98.2%, and there is no room for any optimization. Then there is a buckling check, but there's not a check for the buckling, but this is a buckling multiplier that, as per the code, it should be as at least 15 times in case of nonlinear analysis and 10 times as per the linear analysis. So we'll see more on the buckling checks in upcoming slides. So once this analysis result shows okay, then you can further go and investigating um, the various check like plates or bolts or welds. So here in bolt checks, you can see that bolts are identified based on their B1, B2, B3. Here you can see in the in-plate connection, we have this in-plate connection currently, and the bolts are designated by its marks like 1 to 10, and each row shows the utilization ratio, the forces carried by these bolts. So these are the grades of the bolt, which is user defined. These are governing load combinations, uh, and here in our case it is LE1, the load case 1. Then FT is a tension force in a bolt. Here you can see the maximum tension force in B6 because we have got end plate moment connection, and the top 5 and 6 number bolts are more stressed, which is obvious. And you can see this is stressed to 61.5 as reported in this particular results. Then there will be a shear force in the bolts, and this is a resultant shear force because shear force are either vertical or horizontal acting simultaneously. So this is a resultant shear force carried out by each bolt. Then this is a plate bearing resistance. Then this is a tension resistance of the bolt, utilization for the tension resistance, then utilization for the shear resistance, and this is a utilization for tension and shear combined check. So this is how the result can be interpreted on a single screen. You need not to go to the output and check the results. It gives the indication on a first screen also. So this is how the bolt results are interpreted. Then there is a stress and check or the result interpretation for the end plate. For example, you can see there in a joint there are various plates. The joints composed of various plates element, and these plates are either end plate, stiffeners. Similarly, in case of members, Idea Statica checks certain distance. The member is checked, say 1.25 times the maximum depth of the member. The flange web of the particular member is checked. So this is reported here. You can see the column part is checked, column top flange, column bottom flange, column web, beam bottom flange, top flange, beam web, and this is a end plate. In our case, in this particular connection, the governing part is a end plate, and which is 0.2% of the strain, which is reported here. So this is how the results are interpreted for the strain and stresses in the Idea Statica. This is particularly the maximum equivalent stress reported here. You can see in our case it is not exceeding to 75, which is a grade of our steel. Here the equivalent plastic strain, which we have seen here, which is zero point 0.2 maximum. This particular is a contact stress, and this contact stress is just around the bolt, which is also not exceeding. So this is how the plates results are interpreted in Idea Statica. And once this check is satisfied, all other checks with respect to the formula based software get automatically satisfied, which I have already explained you while differentiating these two approaches. Then the result interpretation for the weld check. Similarly, the weld check also you can see on a first screen also of Idea Statica, where you can see the end plate. The items are highlighted here, and it is connected to the other items. So, for example, end plate is attached to the beam bottom flange. End plate is attached to the beam top flange. End plate is welded to the beam web. So everything is shown here, and here there is a blank space, as you can see, because our beam is welded to the end plate with the CJP weld. So this need not to be checked, and that's why these columns are blank. Whereas other checks for where there is a weld, you can see here the fillet welds are there. End plate is connected to the beam web with 4 thick both side fillet weld, and this check is performed. You can see the in our case it is 87.3, where which is reported correctly 87.3, and this check is performed. All the clauses are reflected here while checking the weld check. You can see that in detail calculation report, all these checks is visible. Lastly, we can see the buckling check or the buckling resistance. So what is buckling resistance? So as per the code, the buckling multiplier, which is shown here in our case, it is a 15.23. So as per code or European code, the buckling factor for the members should be at least 15 and above. So you can see the member buckling because of the forces is in a first mode shape. The web is buckling, and which is reported as a 15.23. The rest all the shapes mode shapes are above 15. So the critical always is a mode shape 1. From list is reported first, and you can see it is increasing. So here there is a there is a demonstration by Idea Statica in laboratory, that the connection plates or the plates element, which is a part of connection, this particular values can be taken as a 3, and need not to be satisfied this stringent 15 uh, 15 This is a dimensionless multiplier. So in Idea Statica, this once this is satisfied, we can safely conclude that our connection is satisfied. This particular check for the member has already been done in our analysis software, so you can omit it also. But there are some instances where we need to consider this check, and we will see in our next videos that how to interpret the buckling check in our connection design. Here there is a nothing exceed 3. For example, these are the hunches where the mode shape 5, which is reporting 31, and 36, which is far more than the uh, target 15. Actually, it is not a 15 for the plates and the connection elements. It is 3, and we will see more on this particular check in our upcoming videos. So that's all the introduction to the Idea Statica, and let's explore together more in upcoming videos with Idea Statica connection design. If you like this video, please subscribe this channel so that you won't miss this series of videos. Thank you.